Hello and welcome to another one of our online lecture videos for differential equations. Today we're going to be talking about matrices, mostly matrix operations, and linear systems along with those. We're just going to start off jumping into some examples. A matrix is just an array of these values. So here we have a couple 3x3 matrices. We have A, we have a first row, a second row, and a third row. We also have a first column, second column, and third column. Same idea with B. And in any row and column position is an entry, and here we notice those entries are constants. And we're going to talk about how we can multiply a constant to a matrix, how we can multiply matrices together, how we can add matrices together, and we're just going to get sort of a rough idea. This isn't by any means going to be a linear algebra course, but we do have to work with some matrices in the upcoming sections, so we are going to introduce the things that we need there in that regards. So first, I want to find 3a minus 2b. So what I can do to start is I can actually talk about what 3a would look like. And multiplying a number to a matrix isn't too terrible at all. What I want to do is I want to multiply every single entry by that coefficient. So 3 times A means first in the upper left I want 3 times 7, which is 21. And if I want to finish off that row, then next would be 3 times 3, which is 9. And 3 times 4 gives me 12. For the second row, 3 times 1 gives me 3, 3 times 0 gives me 0, 3 times 5 gives me 15. And for this bottom row, 3 times 2 gives me 6, 3 times negative 1 gives me negative 3, and 3 times 4 gives me 12. Now I want to subtract away 2b. What I like to do is I like to actually find negative 2 times b and sort of rethink this entirely as 3a plus negative 2 times b. And that's really true of subtraction in general. You can think of it as just adding with negative coefficients. But so I like to sort of include that minus sign right in my work. So let's find negative 2 times b. So now I go over to matrix B and I multiply every single entry by negative 2. So negative 2 times 5 gives me negative 10. If I want to finish that row, negative 2 times 6 gives me negative 12. Negative 2 times 8 gives me negative 16. And for the second row, I'm going to get negative 10, negative 4, negative 18. And then lastly, in this bottom row, I'm going to get negative 2, I'm going to get negative 4, and I'm going to get 0. And what I want to do from here, now that I actually have 3a and negative 2b, is just add them together. So 3a minus 2b. Now in order to add two matrices together or to subtract matrices, I need to make sure that they're exactly the same size. So the same number of rows, the same number of columns. And then we just go ahead and, in this case, we're going to add the corresponding entries. Now if you just did 2 times b, you would subtract. But I said I like to rewrite it so it's addition anyways. So I want to add corresponding entries. So upper left, I want 21 plus negative 10, which gives me 11. And then I'm going to want 9 plus negative 12, gives me negative 3. And then 12 plus negative 16 gives me negative 4. So hopefully this makes sense what's going on. I'm just adding the corresponding entries. So for the second row, I would do 3 plus negative 10 gives me negative 7. 0 plus negative 4 gives me negative 4, and 15 plus negative 18 gives me negative 3. And now for this bottom row, 6 plus negative 2 gives me positive 4, negative 3 plus negative 4 gives me negative 7, and 12 plus 0 gives me 12. So this would be 3a minus 2b, or I sort of tried to re-envision it as 3a plus a negative 2 times b. Next, we're going to talk about multiplying matrices together. So the next thing that I'm asked to find is a times b. And for this, I'm going to write the matrices right next to each other. So a, and then b. Let me go back and see what they were. So a had the row 7, 3, 4. and then 1, 0, 5. Let me scroll up here again. 2, negative 1, 4. And then B had 5, 6, 8, 5, 2, 9 for the rows. 5, 6, 8, 5, 2, 9. And then 1, 2, 0. Now, when we talk about the size of a matrix, and again, I'm not trying to turn this into a linear algebra course, so we're going to sort of talk about these ideas quickly. We would talk about the number of rows first, and then the number of columns. So in this case, we have square matrices, 3 by 3 and 3 by 3, but otherwise we would say that we have n by n sized matrices. And in order to multiply two matrices together, I would need, sort of writing it out in sort of a shorthand notation, I would need these innermost values to match up. So I can multiply an m by n matrix times an n by p matrix, and the result, since these middle values line up, would give me sort of the outer values. The size of the product would be m by p. And what we're really saying is that if this first matrix has m rows and n columns, and the second matrix, or the matrix that falls to the right of this, has n rows and p columns, that I need the number of columns of the leftmost matrix to match up with the number of rows in the rightmost matrix. Now in this case, it really doesn't matter because they're the exact same size. So multiplying a 3 by 3 times a 3 by 3 will give me another 3 by 3. And I'm not going to give you any trick questions or anything kind of nasty like that. But it is important to keep in mind, or at least to discuss briefly, about when we can and when we can't actually compute the multiplication. Let me actually get rid of this because I feel like I'm going to need even more space probably. You know how crazy I get, right? I need to make sure I got enough room so I'm not even going to close it yet. I'm going to wait and see what this first result looks like. Multiplying matrices is a lot of fun. We use what's known as the row-column rule to multiply matrices. And let me sort of illustrate it this way. I want to go to this first row in my first matrix A, so the leftmost matrix is what I mean, and I want to fix that. And then I want to go to the first column of that rightmost matrix. And I want to multiply corresponding entries together. So the first entries would be 7 and 5. And I want to multiply them. 7 times 5 gives me 35. And then I want to add to this, now I want to multiply the second entries. 3 times this 5, the other 5, gives me 15. And then keep going. And then I have 4, the last entry is 4 and 1. 4 times 1 gives me 4. Now what I do, take a breath, I'm sticking with this first row of A, but now I'm going to move to the second column of B. And I go through this process again. So now I want the first entries. 7 times 6 gives me 42. Plus 3 times 2 gives me 6. And then the last entries, 4 times 2 gives me 8. And now I'm sticking with that first row of A, but now I'm moving to the third and final column of B and going through this again. So here we have 7 times 8, what is that, 56? Something like that. 3 times 9 gives me 27. And then the last entries, 4 times 0 gives me 0. So I did need a lot more space. So I'll safely close the matrix now. Now what I want to do, switch to a different color, is I want to go to matrix A. I've exhausted all of my possibilities using that first row of A. Now I'm going to go to the second row of A and back to the first column of B. I'm going to do this process all over again. And this is going to build my second row of product matrix A times B. So the first entry is 1 times 5 gives me 5. Plus 0 times this other 5 gives me 0. And then this last entry, 5 times this last entry, 1. 5 times 1 gives me 5. Now I'm going to stick with the second row of A, but now I'm going to move to the second column of B and do this all over again. So now first entry is 1 times 6 gives me 6. And 0 times 2 gives me 0. Last entries, 5 times 2 gives me 10. I'm going to stick with this second row of A, but now I'm going to move to the third column of B and do the multiplication there, find those products. So 1 times 8 gives me 8. 0 times 9 gives me 0. And 5 times 0 gives me 0. You probably know what's going to happen next. But now I've exhausted all the opportunities with the second row of A, so I move down to the third row of A and back to the first column of B. And we multiply corresponding entries. The first entries, 2 times 5 gives me 10. Negative 1 times 5 gives me negative 5. Last entries, 4 times 1 gives me 4. Sticking with that third row of A, but now to the second column of B, negative 1 times 6 gives me it's 2, I messed up already, 2 times 6. That's what the eraser is for. Say, well, why does the PDF even have the eraser? Our professor is great. It's like, well, no, we need the eraser sometimes. 2 times 6, the first entries, 2 times 6 gives me 12. Negative 1 times 2 gives me negative 2. I'm just human. 4 times 2 gives me 8. Sometimes I do a really good job. And sticking with that third row of A, now it's that third column of B. And let's see what we get here. So 2 times 8 gives me 16. Make sure it's actually writing. Yeah. Second entries, negative 1 times 9 gives me negative 9. Last entries, 4 times 0 gives me 0. So I have all of the work here. So now all I have to do, I got more pages, of course. But now all I have to do is go through the rest of the arithmetic that's left and write that final result as a 3x3 matrix. So here, what do we got? 30 and 10 is 40, and 50 and 4 is 54. We got 42 and 10 is going to give me 52. Oh, sorry. Nope. 42 and 8 is 50, and 6 is 56. Yep. Who's watching? We got 56 and 27, so 70, 83. 5 and 5 is 10. We got 16. We got 8. Yeah. 10 minus 5 is 5 and 4 is 9. 12 minus 2 is 10 and 8 is 18. 16 minus 9 is going to give us 7. Looks good. Okay. So this was A times B. So far, we did this, we did this. I want to find B times A. But hold on a second. Isn't B times A just a funny way of saying A times B?
No.
With matrices, and we're actually going to see this, with matrices, the order that we multiply really does matter. So if I want to find B times A, I have to set up for it, which means B should be at the left, and A should be at the right. So I'm going to write B here, so that has rows 5, 6, 8, 5, 2, 9, 1, 2, 0, and then A, that's 7, 3, 4, 1, 0, 5, 2, negative 1, 4. Call me. Just kidding. They're matrices. It's not a phone number. It is not a phone number. Try it though. Let me know who answers. All right. I'm going to set up for my matrix. We already sort of introduced that row column rule, so maybe let's go a teeny bit faster so we can move on to neon bluer pastures. First row of B, first column of A. We've got 5 times 7, so that's going to give me 35. 6 times 1 is going to give me 6. 8 times 2 is going to give me 16. Stick with that first row, but move to the second column here of that right side matrix. 5 times 3 is going to give me 15. 6 times 0 is going to give me 0. 8 times negative 1 gives me negative 8. And now staying with that first row, but moving to this third column. 5 times 4 gives me 20. 6 times 5 gives me 30. 8 times 4 gives me 32. We'll switch colors. Let's do pink. So now on to the second row of matrix B. and back to the first column of A. Multiply those corresponding entries. First entry is 5 times 7 gives me 35. 2 times 1 gives me 2 for the second entries. 9 times 2 gives me 18. Moving to that second column, 5 times 3 is going to give me 15. 2 times 0 is going to give me 0. 9 times -1 is going to give me -9. Staying with the second row, but on to the third column. 5 times 4 is going to give me 20. 2 times 5 is going to give me 10. And 9 times 4 is going to give me 36. What's a good color here to contrast? We'll just do red. So now we're on to the third row of B and back to the first column of A. First entries, 1 times 7 gives me 7. Second entries, 2 times 1 gives me 2. Third entries, 0 times 2 gives me 0. Stay with that third row, but move to the second column. 1 times 3 gives me 3. 2 times 0 gives me 0. 0 times -1 gives me 0. And sticking with the third row, but now to the third final column, last bit of operations. First entries, 1 and 4, multiply them gives me 4. Second entries, 2 and 5, multiply them gives me 10. Whoa! Put me back in the corner. I don't want to be full screen. That was kind of scary. All right, so sorry about that. 2 times 5, I'm just trying to multiply to get 10. 0 times 4 gives me 0. Don't tell my boss that happened. My teacher came at me. He made himself like all big, like when a cat sort of like poofs up to try to scare someone. So I wasn't trying to be threatening there. I was trying to do math. I don't know if that's a crime. If it's a crime, then I guess it shouldn't be. Oof. We like to have a good time, right? I think we're having a pretty good time. I think it could be way worse. I hope that never ever happens again. If it does, then I think I'm just going to quit. I don't know what to even do with myself. But we can add, right? 35, 6, and 16. What is that? 57. We got 15 minus 8 is going to give us 7. 30 and 20 is 50. 82 then. 82, sure. We can add some more. 18 and 2 is 20, and 35 is going to give me 55. 15 minus 9 is 6. 20 and 10 is 30, and 36 is 66. 7 and 2 is going to be 9. We got 3. We got 14. And this was B times A. And we can verify that these things are not the same because we did A times B. Just look at the first entries. 54, 57. For two matrices to be equal, they have to be exactly equal, meaning it literally has to be the same exact thing. So each entry has to line up. The fact that even one of the entries is off immediately means products are not the same. So I think we learned a valuable lesson. First of all, don't do the thing with the stylus that I did to make yourself all large, because that is alarming when you're tucked away here in the corner and trying to focus on like the mathematics. But the second thing that we learned, and maybe the more important thing, is that when we multiply with matrices, it is not commutative. The order matters. A times B and B times A are not the same products necessarily. Can they give the same thing? Sure. Will they? Probably not. It depends. We got one more thing to do, right? For this set of problems, we want B minus T times I sub 3. Let's talk about this. And this is all the space I have, so let's talk about it carefully. I sub 3, capital I means the identity matrix. The subscript refers to the size. An identity matrix always has to be square. That's why I only see one number there. I sub 3 means the 3 by 3 identity matrix. And for the identity matrix, we have 1s on the main diagonal from upper left to bottom right. So 1, 1, 1. And all the other entries of the 3 by 3 matrix will be a 0. And then, for example, I'll do this in a different color so it doesn't look like I'm trying to introduce this into the example, but just for mentioning the identity matrix of size 2, it's a 2 by 2 matrix, 1's on the main diagonal, 0's everywhere else. So that's what that notation is. Here where we want to find b minus t times I sub 3 means I would take matrix B, which I got to go rewrite it. What was matrix B? 5, 6, 8, 5, 2, 9, 5, 6, 8. I'm still nervous about that, like when I got all crazy like that with the window expanded. I'll never live that one down. Let me know on Piazza if you saw that happen. I want to know if you're watching these videos or if it really doesn't matter what I do. But I think it does. I think you're watching them. So we have matrix B minus t times the identity of size 3 by 3. Now, what's going to happen when we do this is we're going to take matrix B, so I'm rewriting it, of course, again. This is the life that I chose. And what you can do, and let's talk about subtraction, because it's really not difficult to subtract matrices. If we're comfortable with the subtraction algorithm, I can bring t into the identity. So minus, but let me bring the t in. All about the t, we're going to spill the t today. If I multiply t in, well, first of all, t times 0 gives me 0. So wherever there is a 0, it's going to stay the same. But then t times 1 gives me t. So it just kind of presents t on that main diagonal. And when I go through the subtraction, what's going to wind up happening is I'm going to see that anything that isn't on the main diagonal, I'm subtracting 0. So I'm going to skip over the first. I'm going to get 6 minus 0, still 6. 8 minus 0, that's still 8. 5 minus 0 is still 5. I'm going to skip over. 9 minus 0 is still 9. 1 minus 0 is 1. 2 minus 0 is 2. But anything on that main diagonal, I am going to have to do the subtraction. 5 minus t is going to give me 5 minus t. In the middle, 2 minus t gives me 2 minus t. And here in the bottom corner, bottom right corner, 0 minus t gives me negative t. So this would be the result. We're going to need this when we start talking about things like eigenvalues, eigenvectors. So right now we're just introducing it as sort of matrix operations, just sort of for fun, to be honest. So that's our b minus ti, and now we are done with, we did all of these things that we were asked to do. What's next? We're going to talk about product rule for differentiation, and we can still talk about, these things in calculus with matrices. So we're going to verify the product rule, and it says AB, its derivative, is the same as A prime B plus A times B prime. However, when we see product rule in like a Calculus 1 course, we sort of have the advantage of, we could say FG prime plus GF prime, or we could move the terms around and say G prime F plus, F prime G. So that really wouldn't make a difference. But here, the order of the multiplication is important. So I want to be sort of careful with that with matrices. But otherwise, I think this should be really fun. So let's do the left side first, which means first multiply A times B and then differentiate the product. So A times B, how is that going to look? Well, let's write them next to each other. E to the t, that's a t, and then a t squared. We have negative t, 0, 2, 8t, that's a negative 1, and that's a t cubed, times b, which is 3, 2e to the minus t, and 3t. And I want to multiply these together. And here we're going to use that row column rule again, except we only have the one column. So it's going to be kind of a little bit easier to maybe manage. I'm going to fix this first row and multiply through to the column. So first entries, 3 times e to the t is 3e to the t. T times 2e to the minus t gives me, so I'm adding, 2te to the minus t. And last entries, t squared times 3t, and I'm adding this to it, gives me a 3t cubed. And then I want to get yellow to close my matrix so it looks professional for you. Nice. And then we move on to that second row and through the column, adding the products along the way. Negative t times 3 gives me negative 3t. 0 times 2e to the minus t gives me 0, so we're adding. And then 2 times 3t gives me plus 6t. And then now to this last row of A, and back through the column vector that we have here. So 8t times 3 gives me 24t. Here we have negative 1 times 2e to the minus t gives me negative 2e to the minus t. And t cubed times 3t gives me a 3t to the 4th. And I can fix that 4. And one other thing, that exponent. Notice here this middle entry, so instead of rewriting it, negative 3t plus 6t is just going to give me 3t. So I can combine those like terms. So as a negative 3t plus 6t just gives me positive 3t. Now, what I want to do is I want to check this against the right-hand side. Okay, so I want a prime b plus a b prime. So a prime b plus, sorry, a b prime. Yes. Okay, well, let's do this in steps. So let's start with a prime b. So I have to find a prime and then multiply this to b. And here I can sort of cheat because I have b written right here. That was 3, 2e to the minus t, and 3t. For a prime, I'm literally going to go and differentiate each of the entries. So for that first row, derivative of e to the t with respect to t is e to the t. Derivative of t is 1. Derivative of t squared is 2t. Derivative of negative t is negative 1. Derivative of 0 is 0. Derivative of 2 is 0. And then for that last row, derivative of 8t is 8. Derivative of negative 1 is 0. Derivative of t cubed is 3t squared. Let's multiply this now. So e to the t times 3 gives me 3e to the t. 1 times 2e to the minus t gives me 2e to the minus t. And 2t times 3t gives me a 6t squared. Negative 1 times 3 gives me negative 3. 0 times whatever gives me 0. 0 times whatever gives me 0. And then at the end here, 8 times 3 gives me 24. 0 times 2e to the minus t gives me 0. 3t squared times 3t gives me a 9t cubed. Okay, not so bad. But now I have to find, so I can add them together, a times b prime. So here I'm going to rewrite a and multiply by b prime. And I can actually do b prime first. I can cheat because b is right up here, so I don't have to look all the way up. If I find b prime, I'm just differentiating each term and leaving it where it is. So 3 has derivative 0. 2e to the minus t, by chain rule, has derivative negative 2e to the minus t. And the derivative of 3t is 3. And now I just have to rewrite a. So that was e to the t squared. And then what was it? It was negative t, and then 0, 2. And 8t, negative 1t cubed. Going through that row column rule, again, e to the t times 0 gives me 0. T times negative 2 e to the minus t gives me negative 2t e to the minus t. And t squared times 3 gives me 3t squared. Don't you dare. Negative t times 0 gives me 0. 0 times negative 2 e to the minus t gives me 0. And 2 times 3 gives me 6. 8t times 0 gives me 0. Negative 1 times negative 2e to the minus t gives me positive 2e to the minus t. And 3 times t cubed gives me 3t cubed. Now we showed all of our work here, but what I want to do with this is I want to add these things together. So I want a prime b plus ab prime and I could have cleaned these up, I didn't, but let's talk about adding these together. So when I add here, I'm adding the first rows together. So 3e to the t has no like term, so I'll start by writing that. 3e to the t. Then I have, so these are kind of like terms, but I can't really, I mean I could factor with them, but I'm just going to write them out. That's a 2e to the minus t minus 2te to the minus t. And then here I have 6t squared plus 3t squared. And those I can add together. It's going to give me 9t squared. Adding in the second rows, so negative 3 plus 6 gives me positive 3. And then adding here at the very end, I have 24, I have 2e to the minus t. But then these last terms I can actually add together. 9t cubed plus 3t cubed gives me 12t cubed. And let's compare this against what we found for a times b prime, where we multiplied first and then differentiated. So first, 3e to the t plus 2e to the minus t minus 2te to the minus t plus 9t squared. Whoops. Yeah, 3e to the t. Oh, where did... Here it is. Where is it? Oh, man. I'm so sorry. Today's not my day, is it? If you're watching this video, let's put a note on Piazza to cheer me up. Because I found a times b, right? And I found a prime times b, and I found a times b prime. I added these together, so I actually have the right-hand side here, but I never differentiated this. So how can I verify it? Well, we're going to differentiate it right now. We're going to fix this. We're going to make it all better. Because it's going to be really hard to compare them if I never do ab prime, but I'm not giving up. We're going to have a good time. We got a little bit more work left to do, and then we can verify these. So let's differentiate this first row. If I take the derivative of 3e to the t, gives me 3e to the t. Here I need product rule, so I'm going to rewrite 2t. Derivative of e to the minus t is e to the minus t times minus 1, plus, now I'm going to rewrite e to the minus t, derivative of 2t is 2. And then here the derivative of 3t cubed is going to give me 9t squared. Second entry, a little bit nicer, right? Derivative 3t just gives me 3. And then here for this last entry, derivative of 24t is 24. Derivative of negative 2e to the minus t. Chain rule is going to flip the sign on that coefficient, so we get plus 2e to the minus t. And then derivative of 3t to the fourth gives me 12t cubed. Okay, well now we can check, thankfully, right? So 3e to the t minus 2te to the minus t plus 2e to the minus t plus 9t squared. Looks like what I got here, all the same stuff. Middle entry should be a 3, whoops, 3, and then what, 24, 2e to the minus t, 12t cubed, 24, 2e to the minus t, 12t cubed, looks great. So now we have successfully verified our product law for differentiation with matrices. Oh, and I guess I just did one, I only needed one piece of the, so here we just have an extra page now for notes. Need more coffee. Do you like the hot coffee or do you like the iced coffee here too? Iced coffee, hot coffee, both. Need more of it. All right. Back in it to win it. Let's move on. Let's talk about writing a system in the form x prime equals p of t times x plus f of t. And there's a certain nomenclature that I want to introduce for this. So we're going to say x is a vector with entries x and y, so a column vector with entries x and y. And it follows from that that x prime is going to have entries x prime, y prime. It's maybe a bit strange to name this vector x and for one of the entries to be x and the other entry to be y, but that's the sort of the standard notation that we're going to use. And if I want this to have more entries, well, I can just write more entries in underneath as well. So what I want to do to try to write my system in the form x prime equals p of t times x plus f of t, where p of t is going to be a matrix and f of t is going to be a column vector, we just want to start very slowly. So we'll say x prime is equal to this vector with entries x prime, y prime. And with these equations that I'm given, I can substitute. So x prime, I can replace it with, in this first entry, 2x plus 4y plus 3e to the t. Y prime, my second entry, I can replace it with 5x minus y minus t squared. And now what I want to do is I want to actually separate the function of t for f at t out from this. So I want to keep the x and the y terms where they are for now. But then I want to break away from this and add a vector with my function of t in it, which is 3e to the t for that first entry and negative t squared for that second entry. And then what am I supposed to have here? Well, it's 2x plus 4y still, and 5x minus y. So here I've actually decomposed this vector into a vector plus another vector. That's sort of the idea. But what's really fascinating about this is with this first vector that I have, I can rewrite this as a matrix times a vector with entries x and y. I don't want to forget about my vector here with my function of t in it. But when I do this, what I'm left with behind is really just the coefficients in the order that they appear. So we call this a coefficient matrix because it leaves those coefficients, but I had the 2x and the 4y, so I'm going to have 2 and 4 for this top row. And then 5x minus y, I'm going to have 5 and negative 1. And if you ever want to return back to what we had, all you have to do is undo this step by step. So if I do the row column rule, for example, I have 2x plus 4y back. And here, down to the second row, 5x minus 1y is 5x minus y. And then I can add these entries in, etc., etc. But what this is now is it's written in the form that I wanted it. So we have x prime equals, this is p of t times x plus f of t. And this is going to be useful when we start talking about eigenvalues and eigenvectors and working with systems with that. So I just want you to sort of get used to writing this in this interesting way. This next example has mentions of x, y, and z. So we're going to modify what we said a little bit. We're going to say x now is a vector with 3 entries, x, y, z. And then x prime has entries x prime, y prime, z prime. That's still the same idea, the same real premise. So we'll start with, very slowly, x prime has entries x prime, y prime, z prime. And I can substitute in here, so x prime, it's y plus z, but I'm going to actually mention the missing term, which is x, so 0x plus y plus z. Y prime is in the middle, that's z plus x, so I'm going to say x first, 0y plus z, since y is missing. And z prime is last to this third row, that's x plus y, and I'm going to say plus 0z since it's missing. Now maybe we're noticing something different about this example other than the fact that I have x, y's, and z's. There's no mention of t. So what would my function of t look like as a vector? Well, sadly it's really not there. If I want to force to show it, it would just be 0, 0, 0. And then remember what we did from here, we can actually split this up even nicer. So I can build a matrix times a vector. My f at t vector is pretty boring since there's no function of t anywhere. It's just the vector 0, 0, 0. But here I'm trying to break this away too. So I have a vector with x, y, and z. And what I'm going to wind up with is a 3 by 3 matrix here. Again, a coefficient matrix. It's going to take coefficients in order 0, 1, 1, 0x, 1y, 1z. Then what do we have? 1x, 0y, 1z. Then we have 1x, 1y, 0z, so 1, 1, 0. And this is going to break this up into that matrix P of t times x plus f at t. Where f at t wasn't really even there, so we see we have sort of a homogeneous system here. And if I ever want to return, just multiply back out with the row column rule. So this first entry would be 0 times x plus 1 times y plus 1 times z, which is just y plus z, which is what I had before. So not too bad. Let's take a look at one more example of this, and then we can move on to some new stuff. This still has x, y, and z, so same idea from before. X is a vector with entries x, y, and z. It follows then that x prime has entries x prime, y prime, z prime. So then x prime with entries x prime, y prime, z prime. I can start slowly substituting with the equations. What is x prime? Well, here it's 3x minus 4y plus z plus t. Y prime is next, that's x. I'm missing y, so 0y minus 3z plus t squared. And next is z prime, that's missing x, so 0x plus 6y minus 7z plus t cubed. And from here we want to sort of keep the same idea, but I want to break away my function of t into its own separate vector. So what are my function of t pieces? Well, for the first entry, it's a t. For the second entry, it's a t squared. And for the third entry, it's a t cubed. Kind of cute, right? Now, what did I leave behind? All the other stuff, right? 3x minus 4y plus z. Here we have x plus 0y minus 3z. Here we have 0x plus 6y minus 7z. And into its final form, now I can write this as a coefficient matrix times a vector with entries x, y, z plus my vector with my function of t in it, which I already know is t, t squared, and t cubed for those elements. Remember, the coefficient matrix just takes those coefficients in order, make sure it's x, y, and z in that order, or else you'll have to shuffle it around. But 3x, negative 4y, 1z, so in that order, 3, negative 4, 1. The next row is going to be 1, 0, negative 3. Last row is going to be 0, 6, negative 7. And now this is written in the form matrix P of t times x plus our function f at t. So just a new way of writing a system using matrices. Let's take a look at a couple of examples that start to touch on what we're going to be talking about in the next lecture. Here I want to verify that the vectors are solutions to the given system. Then I want to use the Wronskian to show that they're linearly independent solutions, and then I want to write the general solution to the system. So here we're saying x prime is equal to this matrix times x, or in general, x prime is equal to a times x. So what we're saying is, if I take this matrix A and multiply it to one of these vectors x, it should produce the derivative. And let's see if that's true. So here for x sub 1, a times x sub 1 would be this matrix 4, 2, negative 3, negative 1 times this vector 2e to the t, negative 3e to the t. And if I multiply this together, what do I get? We'll do that row vector rule, that row column rule. 4 times 2 gives me 8e to the t. 2 times negative 3 gives me negative 6e to the t. And then here for the second row, negative 3 times 2, that's negative 6 e to the t. And negative 1 times negative 3 gives me positive 3 e to the t. And these are like terms. So if we combine them, 8 minus 6 gives me 2 e to the t. And negative 6 plus 3 gives me negative 3 e to the t. But I want you to notice that this is what we would get if we differentiated x sub 1. If I took the derivative of 2 e to the t is 2 e to the t. Derivative of negative 3 e to the t is negative 3 e to the t. So that checks. I want to do the same for x sub 2. What is a times x sub 2? Well, matrix A is the same. That hasn't changed, of course. But that vector x sub 2 is e to the 2t negative e to the 2t. So let's multiply these out. See what this gives me. So here multiplying, I get 4 e to the 2t, and then I get minus 2 e to the 2t. Now down to the second row, negative 3 times e to the 2t, and negative 1 times negative e to the 2t is plus e to the 2t. And if I combine these like terms, well, 4 minus 2 gives me 2 e to the 2t. Negative 3 plus 1 gives me negative 2 e to the 2t. And this, I think, is pretty interesting, because if I were to take the derivative of x sub 2, derivative of e to the 2t is 2 e to the 2t. Derivative of minus e to the 2t is minus 2 e to the 2t. So this is the same as if I just differentiated that vector. So we verified that both of these are solutions to x prime is the same as a times x, where if I do a times x sub 1, that's the same as x sub 1 prime. If I do a times x sub 2, that's the same as x sub 2 prime. Now to verify that these are linearly independent, I want to use the Wronskian. So the Wronskian is going to be the determinant of, in this case it's a 2 by 2 matrix. I want to take x sub 1 as my first column and x sub 2 as my second column. Now before, when we saw the Wronskian for functions, we ended up working with derivatives. So we would have a first row fg and then f prime g prime. I don't need that. And that was really to ensure that we had a square matrix, right? If I just put the functions in there, then I only have one row. So in order to build it so we have a square matrix, we had to include some derivatives, and that was the idea that we had of the Wronskian before. But since I have these column vectors, I want to take these vectors and just write them in as columns. So x sub 1 is 2 e to the t negative 3 e to the t. And x sub 2 was e to the 2t negative e to the 2t. And here I have a 2 by 2 matrix that I want to find the determinant of. So remember, we multiply along the main diagonal, so that's 2 e to the t times negative e to the 2t, and we subtract the product on the off diagonal, which is e to the 2t, times negative 3 times e to the t. Well, what is this going to give us? Well, if I multiply it out, it's going to give me a negative 2, and here we would add the exponents since we're multiplying, so e to the 3t, minus a negative becomes plus 3, and then e to the 2t times e to the t, that's e to the 3t. We add the exponents since we're multiplying. And these are like terms, so 3 e to the 3t minus 2 e to the 3t gives me e to the 3t. And what can we say about this? Well, if we remember, with the Wronskian, if I want to use the Wronskian to show that something is linearly independent, I want to show that the Wronskian is non-zero. And what did we get for our Wronskian? We got e to the 3t. Well, e to the 3t as a function for no real value of t can be equal to 0. So we say since the Wronskian is non-zero, x sub 1 and x sub 2 are linearly independent. I have some extra space here because there's one more thing I have to do. I have to write the general solution of the system. And the general solution is going to be x at t equals c sub 1 times x sub 1 plus c sub 2 times x sub 2. But here x sub 1 and x sub 2 were these vectors. So let's bring those vectors back in. X sub 1 was 2e to the t and negative 3e to the t. And x sub 2 was e to the 2t, negative e to the 2t. And we can go ahead and bring the coefficients in. Say, okay, this is 2c sub 1 e to the t, negative 3c sub 1 e to the t, plus, here I can bring c sub 2 in. So c sub 2 e to the 2t, negative c sub 2 e to the 2t. And lastly, as sort of a nice notation, I can even add them together into one vector. So adding the top entries, 2c sub 1 e to the t, plus c sub 2 e to the 2t, and adding the bottom entries, negative 3c sub 1 e to the t, minus c sub 2 e to the 2t. And this is perfectly fine to leave an answer, but what we sometimes like to do is break this into x sub 1 of t and x sub 2 of t, and we do this by row. So x sub 1 of t is this top row, which is 2c sub 1 e to the t, plus c sub 2 e to the 2t. X sub 2 would be this bottom row, negative 3c sub 1 e to the t, minus c sub 2 e to the 2t. And here we have these two solutions to the system, to our first order system. Let's see another example of this. We'll go through this a little bit quicker, and we'll take a look at a 3x3 system for this. So are you ready? Let's take a look at it. I want to show that x prime is equal to a times x, where a is this matrix with rows 0, 1, 1, 1, 0, 1, 1, 1, 0. Let's start with x sub 1, which is e to the 2t for every entry. If I multiply this with the row column rule, I get 0, e to the 2t, e to the 2t, which combining gives me 2e to the 2t. See, I'm being careful now, right? Next, we get 1 e to the 2t, well, 1 times, and then 0 times e to the 2t is 0. 1 times e to the 2t is e to the 2t, so this also gives me 2e to the 2t. And then here, 1 times e to the 2t is e to the 2t. Another 1 times e to the 2t is e to the 2t. And then 0 times e to the 2t is 0. Combining, adding, we get 2e to the 2t. And this is the same thing that we would get if we would have differentiated this vector. With chain rule, would give 2e to the 2t for all of these entries. Okay, well, let's try it with vector x sub 2. If you're so sure, let's try it with vector x sub 2, which is e to the minus t, 0, minus e to the minus t. Let me sort of go through this a little bit faster. We're going to get 0, we're going to get 0, we're going to get negative e to the minus t. Next, we're going to get e to the minus t, 0, negative e to the minus t. So everything's going to cancel, so that gives me 0. Next, we're going to get e to the minus t, 0, and 0, so e to the minus t. And this, hopefully, is what we get if we take the derivative of x sub 2. We get e to the minus t times negative 1, we get 0. Negative e to the minus t times negative 1 becomes positive. So that's exactly what we would get if we differentiated x sub 2. We get the same effect by multiplying the matrix times x sub 2. Okay, well, I know what you're thinking. What about x sub 3? Let's try it. And x sub 3 had entries 0, e to the minus t, and negative e to the minus t. We'll multiply this out quickly. We get 0, we get e to the minus t, negative e to the minus t cancels, so we get 0. Next, we get 1 times 0 is 0, 0. We get negative e to the minus t. Next, we get 0, e to the minus t, and 0, so e to the minus t. but this is exactly what we would get if we took the derivative of x sub 3. So 0, e to the minus t times a negative 1, negative e to the minus t times negative 1 flips the sign back. So all of these are solutions to the system. Now what I want to do is I want to verify that they are linearly independent solutions. So I got to look for the Wronskian. And in this case, we're going to have one of those 3 by 3 determinants, which we took a look at much earlier in the course. But I'm going to build this by putting these as columns to a 3 by 3 matrix. So the first column is e to the 2t, e to the 2t, e to the 2t. Second column is e to the negative t 0 and negative e to the negative t. And the third column is going to be 0, e to the negative t, negative e to the negative t. And I want to find the determinant of this 3 by 3. Here we're just going to use a traditional cofactor expansion across that top row. So I'm going to bring out e to the 2t times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. So that's the sort of lower right, 0, e to the minus t, negative e to the minus t, negative e to the minus t. I bring out that next entry. I have to flip its sign because of that checkerboard pattern. So that's negative e to the minus t times the determinant of the 2 by 2 matrix when I remove that entries row and column. So this kind of splits it. So here we're looking towards the bottom. We have e to the 2t, and then we jump over to e to the minus t. Underneath, we have e to the 2t. We jump over to negative e to the minus t. And for the last bit of the cofactor expansion, I would bring out the 0. So we'd say, okay, plus 0 times the determinant of the 2 by 2 matrix. But I don't really care what this even is, because I'm going to multiply it by 0 anyways. So here it allows me to move through it a teeny bit quicker. And we'll say, okay, here we have e to the 2t times, now the 2 by 2 determinant, we know how to compute this. Multiply on the main diagonal gives me 0 minus e to the negative t times negative e to the negative t. And then here I have this minus e to the minus t from my checkerboard pattern. Multiplying here, we get negative e to the 2t times e to the negative t, and then minus the product on the off diagonal, that's e to the minus t times e to the 2t, and the rest of this was 0 anyways. Let's keep going with this. So we have e to the 2t times double minus sign switches to addition, and here we get e to the minus t times e to the minus t is e to the minus 2t. I add those exponents. We have minus e to the minus t times, here if we add the exponents, we get e to the positive t, and I have that minus sign in front, so minus e to the t, minus, here I have another e to the t. So, e to the 2t times e to the minus 2t, and then here we have minus e to the minus t times, what is this? It's a negative 2 e to the t. Now let's work through this. So here we're multiplying, so we would add the exponents. So this gives me e to the power of 0. Minus a negative is plus. I have a 2, but then e to the negative t and e to the t give me another e to the 0. So what is this? Well, this is 1 plus 2. This gives me 3. And this is successful as well, right? The Wronskian in this case is non-zero. 3 is not equal to 0. So we say, okay, since the Wronskian is not 0, then these are linearly independent. x1, x2, and x3 are linearly independent. And we can write that general solution. So we'll say, okay, x is equal to c sub 1 x sub 1 plus c sub 2 x sub 2 plus c sub 3 x sub 3 in this case. Yeah, I know, I'm in the middle of something. Cool, we're doing cool stuff. x1 was e to the 2t, e to the 2t, e to the 2t. This was e to the negative t, 0, negative e to the negative t for x sub 2. And x sub 3 was 0, e to the minus t, minus e to the minus t. We bring those coefficients in, then we write them row by row. Let me sort of skip over some of the in-between stages just to cut down on time and write down these individual pieces. Top row, what are you? You're a c1 e to the 2t plus a c2 e to the minus t plus 0. Middle entries, where are you at? That's a c1 e to the 2t. That's a 0. And then that's a c sub 3 e to the minus t. Bottom entries, let me hear you. C sub 1 e to the 2t. We got a minus c sub 2 e to the minus t. And we got a minus c sub 3 e to the minus t. Here we have our solution to the system. We verified it's linearly independent as well. Okay, so a little bit left. I think we can get through this. Now we're just going to talk about initial conditions. So we're not going to verify that these are solutions. We already saw a couple of examples of that. If you want to verify that they're solutions, this would be great practice. So this would be a good practice problem for that part. But we're just going to work with initial values. So let's go right to building our solution. C sub 1 times x sub 1 plus c sub 2 times x sub 2. Here x sub 1 has entries e to the 2t, e to the 2t, and x sub 2 has entries e to the negative 2t, 5e to the negative 2t. And we can bring in these coefficients and split them up row by row into the two individual pieces. So top entries, what are you? You're a c sub 1 e to the 2t plus c sub 2 e to the minus 2t. Bottom entries, what do we got? C sub 1 e to the 2t plus 5c sub 2 e to the minus 2t. And now we work with these initial values. So x sub 1 at 0 is equal to 5. And x sub 2 at 0 is equal to negative 3. Sure, why not? Well, since we're able to split these up by row, and this is sort of, I think, the best way to write it, I can now work with these initial values. So x sub 1, if I plug in 0, remember e to the 0 is 1, so I get c sub 1 times 1 plus c sub 2 times 1, and this is equal to 5. X sub 2 at 0, remember e to the 0 is 1, so I get c sub 1 times 1 is c sub 1 plus 5 times c sub 2 times 1, which is 5c sub 2. And this should be equal to negative 3. Now here I can work with a substitution statement. So here, for example, if I solve this first equation for c sub 1, c sub 1 is equal to 5 minus c sub 2. And we plug that into this second equation. So we get 5 minus c sub 2 plus 5c sub 2 equals negative 3. And then if we go ahead and combine like terms, negative c sub 2 plus 5c sub 2 is 4c sub 2. If I subtract 5 over, negative 3 minus 5 is negative 8. So then c sub 2 is negative 2. And now that I know what c sub 2 is, I can plug in to find c sub 1. C sub 1 is 5 minus negative 2, so c sub 1 then is 7. And now that I know these values, I can go back to my general solution and fill it out. So x sub 1 at t, that's c sub 1 e to the 2t, which is going to be 7 e to the 2t, and then minus 2 e to the minus 2t, right, minus 2 e to the minus 2t, and x sub 2 is going to be 7 e to the 2t minus 2 times 5 e to the minus 2t. So let me fix this then. So we had 7e to the 2t, and then 5 times c sub 2, that's 5 times negative 2 gives me negative 10 e to the minus 2t. So just working with those initial values to get our particular solution. All right, feeling good. We'll do one more example working with these initial conditions. And again, we've seen how to verify that these are solutions. So please go ahead, take the time to verify that these are solutions. But let's just build that generic form for our solution and then build the particular solutions. So here we'll say x is equal to c sub 1 times x sub 1 plus c sub 2 times x sub 2. What is x sub 1? That is 3e to the 2t, 2e to the 2t. And what is x sub 2? That is e to the negative 5t, and then 3e to the negative 5t. And let's break this up into our two separate pieces. X sub 1 at t, I want the top entries, so 3c sub 1 e to the 2t, plus c sub 2 e to the negative 5t. X sub 2 at t, I want the bottom entries now, so 2c sub 1 e to the 2t, and then plus 3c sub 2 e to the negative 5t. And I have initial values. X sub 1 at 0 equals 8, and x sub 2 at 0 equals 0. Okay, let's do it. If I plug 0 in, x sub 1 at 0 gives me 3c sub 1 times 1 plus c sub 2 times 1, and this should be equal to 8. With x sub 2 at 0, I get 2c sub 1 times 1, which is 2c sub 1, plus 3c sub 2 times 1, which is 3c sub 2, and this is equal to 0. So I have these two equations to work with. And up to you which one you want to work with first. For example, here I could work with this first equation, and I could say, well, let me go ahead and solve for c sub 1, for example. So 2c sub 1 is equal to negative 3c sub 2. Dividing by 2, c sub 1 is negative 3 halves c sub 2. And I can use this as a substitution statement in this first equation. So 3 times c sub 1, the c sub 1 is negative 3 over 2 times c sub 2, plus c sub 2 equals 8. So what does this give me? Well, this gives me negative 9 over 2 c sub 2 plus c sub 2 equals 8. But go ahead and get a common denominator. So this is really a 1 c sub 2, or that's a 2 over 2 c sub 2. And if I combine these as like terms, here I'm going to get negative 7 over 2 c sub 2 equals 8. And then I'd want to multiply by the reciprocal. So c sub 2 is equal to 8 times negative 2 over 7. So then c sub 2 is negative 16 sevenths. Well, okay, what about c sub 1 then? Well, I can go back here to my substitution statement and say c sub 1 is negative 3 halves times c sub 2, which is negative 16 over 7. And I can reduce. So here negative times negative is positive. 16 divided by 2 gives me 8. 8 times 3 gives me 24 divided by 7. And now we can drop these into our general solution to get our particular solution for x sub 1 at t and x sub 2 at t. So here I want 3 times c sub 1, so that's, well, we're kind of running out of time anyway, so that's 3 times, don't be lazy like I am, but sometimes it's okay, e to the 2t, and then plus c sub 2, It's negative 16 over 7 times e to the negative 5t. Sure. And then x sub 2 at t, that's a 2 c sub 1. So 2 times c sub 1, I guess I'm not so afraid of that, right? 48 over 7, e to the 2t. I think some fear of arithmetic is normal and healthy. 3 times c sub 2, so that's 3 times negative 16 over 7, e to the negative 5t, right? Did I do it? Am I done? I'm done. I'm trying to make sure I do this before my computer dies. Please write to the university, let them know that I need a better computer. Say, hey, get this guy a really nice computer, and then he's going to start multiplying more numbers for us. That's a promise that I'm going to make to you. Hey, this has been a weird one. I feel like this has been a trying time in the semester. I don't even really have room to write the homework. I'm going to make room for it because we are done with this section. So I'm going to put the homework in the homework jar. Go to the online homework. Take a look at this homework. Let me know what you're thinking about these matrix operations. Let me know what you think about building these solutions. Let me know on our class discussion board. And hey, otherwise, I will see you next time for another show-stopping differential equations lecture. Until then, make sure that you keep learning, keep dreaming, and always follow your heart. And I'll see you soon.